I'm here at Aerospace Bristol, this UK city's landmark aviation museum. It's the home of Concorde Alpha Foxtrot, the last Concorde built and the last to fly. At the upcoming Optica Quantum Industry Summit 2025, we'll dine directly beneath her. If you attended last year, you'll know that the dinner and corridor conversation is what sets us apart. This year, expect a uniquely Bristol backdrop among historic aircraft, but also meaningful conversations with leaders in quantum and photonics. The Optica Quantum Industry Summit will not be shared online. To benefit from frank and open discussions, you need to be at the M-Shed Conference Centre or seated at a table under Concorde. Will you take a seat at the table? This is your last call to influence the future.
In Malaga during the Global Photonics Economic Forum, we heard a keynote from Michael Klug of Google. He gave us a glimpse into the rapidly evolving field of extended reality. On October 28th, we take that conversation further during the Optica online industry meeting on augmented and virtual reality. As XR technology expands into new applications, there's a heavy demand for innovation in headset design, as display performance is accelerating. Developers are pushing to make headsets lighter, more affordable, and visually superior. Companies work hard to offer exceptional image quality while improving field of view, frame rate, and latency. Our meeting will explore how optics and photonics are shaping this evolution through breakthroughs in near-eye displays, waveguides, eye tracking, and sensing systems. Our speaker lineup this time includes Google, EverySight, Letha, IMEC, Solnil, Nexus Photonics, Heteromerge, and Vitria Lab. This 90-minute meeting begins at 10 AM Eastern, which, because of different winter time changes, means we start at 2 PM in the UK and Ireland and 3 PM in Central Europe. That's an hour earlier than usual for attendees in Europe. Sign up for free to participate in our Zoom room to better understand the business prospects in this fast-moving extended reality sector. Your free attendance is possible thanks to generous support from IMEC and ANSYS, who add value to Optica events. The meeting is moderated by Optica's Jose Pozo and Olga Raz. Now let's start the live conversation.
Hello, everyone. Good morning, good afternoon, good evening. This is Jose Pozo, CTO of Optica, reporting live from the Frontiers in Optics conference in Denver, Colorado. And it is an honor. It is an honor to start the meeting on augmented and virtual reality. This is, as the announcing video said, this is a continuation of the conversation that started in Malaga a couple of weeks ago at the Global Photonics Economic Forum with the keynote of Michael Klug. What we want to do today is very simple. We want to make sure that a set of integrators, companies that are key in the ecosystem, such as Google, Everysight, and Expanseo with their AR contact lenses, share with us what we can do for them. And then we have our corporate members, the companies that make this association what it is, a great platform for networking. And our corporate members will actually answer those challenges from the integrators. We have today IMEC, Solning, Nexus Photonics, Heteromerge, Eulitha, and Vitrea Lab, and everyone else in the room. Remember, if you have any comment, question, or address, you can address the challenges presented by the integrators, raise your hand. If you are jealous about the way that we integrate with our members, please make sure you join as a member. Optica.org/join corporate, and then you will be featured in the videos. We will come to visit you. You will have opportunities to show your technology at our events. You can download market reports, everything. Just join us. Join us. We are building a fantastic community of photonics companies. I also would like to remind that we like to meet in person and online. Today, on 20th October, we are talking about AR/VR. On the 4th of November, write your calendars. We have a great event on laser cutting and drilling. And this is the agenda of all our events online until the 17th of March. We also love to meet face to face. A couple of weeks ago, we had the meeting at the PEC Summit in Sunnyvale, California, hosted by Juniper. As you saw in the opening video with John Pugh, we have a great event on the Quantum Industry Summit. Let me say something about this. This event is very different. The quantum companies will actually not say what they can do, but say what the photonics industry can do for them. Share with them their needs on detectors, narrow linewidth lasers, packaging, low loss coupling, fiber to chip, anything that they need, they will share so the photonics companies can help them succeed. This is a very unique event. I hope I can see some of you in Bristol. But now allow me to remind one thing. Look very, very well here because we are live streaming this meeting in YouTube. YouTubers of the world, if you have any comment or question during the meeting, write in the chat and I will read it in the room. And this is, of course, valid for the people with me here in the Zoom room. It is really honestly fantastic to see so many of you today. This is a networking event. All you have to do today is to make sure that you contribute to the discussion. So don't stay just quiet. Whenever you see the presentation from Google, from Everysight, from Expanseo, make sure that you have technology that they can use and voice it. Raise your hand and speak or write in the chat what you can do for each other. And now allow me to introduce you to the hosts of this fantastic session for the next 90 minutes. Dr. Olga Ras, Director of Optics at Optica, and Dr. John Pugh, Director of PIC and Quantum Technologies at Optica. Guys, thank you so much for the great job putting this fantastic lineup together. The floor and the attention of the AR/VR community goes to you.
Thank you, Jose. We'll hope to keep up with your excitement, and I am really excited. I am happy to hear first of all, of our incredible speakers in the room. Today, we're truly international. We have people coming from California, those that are currently in Denver, in beautiful Switzerland, Germany, Florence, Israel, and Dubai. It's really an international team, international views, and I'm really looking forward to hear from all our speakers. I'm also excited to see amazing people among our guests and attendees, and it's an Ad Optics, it's 3D IG, it's Incron, and many, many others. So guys, I know you're all experts. Don't hesitate, ask questions. It is a discussion and not a webinar. Everyone welcome. And I would like to really not, without any further ado, to really move on swiftly to our opening speaker. And it's my great pleasure to call to the floor Christophe Perros from Google to share your views and on the horizons, actual status and challenges of the IR and XR world. Christophe, thank you very much for joining us from the beautiful country of cheese, chocolate, and money. The floor and attention of everyone is yours.
Thank you, Olga. Thank you, Jose, and thank you all the Optica team. It's always a pleasure to be here and joining this great event. I'm sharing my screen. Do you see my screen?
Crystal clear. It all runs well.
Okay, so thank you, and thank you also to all the participants. I'm very excited to be with you and hear a lot of the speaker today. So what I'm going to do in the next 6 to 8 minutes is to share a little bit some thought about AI glasses. So I will be a little bit superficial, but I just want to give a glimpse of what's coming and also what we need to make it happen. Let me try to okay, so in Google, our mission is to organize the world information and make it universally accessible and useful. And we're doing through different sorry, I need to move. I see you, Olga, on full screen and not my screen. Okay.
Well, I look good.
Yes, wonderful. But okay, so we're doing it every day by helping billions of people through different application and services powered by AI. I'm sure most of you are using some of this application. We can use YouTube, for example, to follow this event today. One of or is this little icon here, which is the Android. So Android is powered on many devices, you know, on phone. It's an operating system. It's on phone, tablet, watch, TV. And what we did in December 24 is we introduced an extension which makes Android basically fully available for VR, MR, and AR devices. So what's important is because we are all working and discussing today about how to build these devices, but you also need all the software layer, correct? The operating system, the application, etc. So the good news is since a little bit, almost 1 year, we have an operating system now. And another important milestone was a few days ago, where Samsung, in collaboration with Google and Qualcomm, we introduced the Galaxy XR, which is the first Android XR headset. So I really invite you to go on our website, read the note from our Vice President, Shara Mizadi, and you can also order your devices on Samsung. And there's a lot of things important here to notice is, for example, what you can see this image is you have access to Google Map and of course all the ecosystem of Google. So that's a quite important milestone. But we want to go beyond serving with Android XR the VR system. We want to grow the ecosystem to optical see-through AR glasses and AI glasses. And to make this happen, we obviously need devices. And to make devices, you need a display, correct? If you go in augmented reality. So this is a very simplified presentation of how you make your level choice system to build a display. So here I will show you different technology engine, and today some of the speakers like Vitrolab and others will speak about different technology of optical engine. And here you have an optical engine which creates the image, and you have a combiner which basically sends the image to your eye. And you have many different type of optical engine. I just list 5 of them here. Micro OLED, which is highly commercially available, and it is actually used today in a VR system. And in some of the AR headset as well, you have the LCOS, micro LED, laser beam scanner, DLP, and many other engines as we will discuss today. But this engine have different trade-off in terms of brightness, size, and engine power consumption. For example, DLP, which is a very well-established technology, is very bright, but at the same time it's big and it's also consume a lot, which is not what you want when you want to have a pair of glasses. And there's a lot of attraction right now, I would say, on these two technology. One is micro LED, and you can see why, because it's small, it's potentially a low power consumption, it's very bright. So depending on this constraint, you can use different combiner. Most of them are waveguide. You have diffractive waveguide, which are not very efficient, so you need to couple them with a higher brightness engine, and at the opposite you have like bird bath, which is the classical way, which doesn't need too much brightness because it's very efficient. And you have reflective waveguide, which makes a lot of highlights this last few days with some product release. So each of these technology has its plus and minus. We don't need to go through it today, but I think most of the commercial product today are using LCOS. Why? Because it's mature and it has a certain level of efficiency which allow you to use it with most of the waveguide. As I say, there's a lot of excitation here because it's higher brightness potentially and smaller, but it's currently in a development phase. So we will hear more from our speaker today. In waveguide, you also have a lot of different waveguide. I just put three main here. One is a diffractive, where you basically use grating to couple the light in, couple the light out. A lot of development here using 1D, 2D, 3D gratings. We will hear about some of our speaker today, how you can make them. There is also reflective. So this is using embedded mirror. They can be continuous mirror. They can be segmented mirror. Again, a lot of activity here, actually, especially in Europe and also in Israel. And curve waveguide, it's also another technology. So we'll hear about this today. Materials, also a lot of development. If you travel right now in, for example, in Asia, there was a conference and this question came a lot about silicon carbide, So material with very high index are very expensive to do now. So there's a lot of activity on material. And of course, the index, lower you go, you can go to polymer, and there's a lot of development also to bring higher reflective index. So this is also a lot of opportunity. I think some of our speaker will speak about material development today. And obviously, we also have a lot of opportunity in manufacturing. How you can make this structure large area cost effective. So there's tons of development over the last 20 years or even 30 years, for example. I think we just celebrated the 30 years last week or 2 weeks ago of nanoimprint technology. So time fly, and this is really now booming. New material as well. And most important at the end, I would say, is we need all together to work to build this ecosystem. And that's kind of my message today. Is in Google, we want to work with everybody to build this ecosystem and bring this next technology.
Thank
So
you, Krista. So if you're already sharing this call so openly, could you pinpoint the technologies that you believe will make the major difference in the next maybe half a year or year to the performance of the XR and devices?
I mean, it's difficult to point one of the technology itself, especially we have a lot of speaker here which will have maybe different opinion. So if I point one, but I would say, the integration in a glass form factor, whatever can help to miniaturize and decrease the power consumption is something very needed as a combiner level and also at the optical engine level. And of course, at the end of the day, has to bring at a cost effective.
Yes, I wanted to ask you because in your wonderful slide of comparing different technologies, there's one important bar missing: cost. And I think in this, when we ask Google as the person, as the company which has all the opportunities, how much is cost truly important? Would you sacrifice the technology for the cost, or vice versa?
I mean, my answer to you is basically, I would say. So in Google, you see my slide, correct?
Yeah.
So in Google, our intent is to serve billions of people. So it has to be developed for billions of people. So you can ask yourself the question how much you want to pay. Correct?
I think, yeah, it will be strongly depends, right, if we're in Switzerland or somewhere in India, potentially.
But we want to serve everyone. I think that's the message, correct? At term, this is the mission of Google.
Would you say that then maybe in this respect, several technologies can coexist with, let's say, some offering better performance at a higher cost, while others are rather the opposite?
Yeah, I think this is how, every field starts, right? You have different technology and then it will merge to someone. This is, I think, how we will come. The last 2 years, I've seen very, very, very acceleration of the development. Thanks to AI, actually, to be honest, because AI is a big driver, correct? Very good channel for AI. So
And if we speak of the AI, because also XR represents really this opportunity for combining with AI, but at the same time, right, AI also puts a lot of additional requirements for the architecture of the devices, and as you mentioned, power consumption. So what are the sacrifices or what challenges you see in the really merging the two? Will we need a huge power bank or will the to carry with us? Or is the technology evolving in the sense that it all can coexist?
I mean, I think you saw the release of product recently by a competitive company in a right form factor, correct?
Mm-hmm.
So again, it has to be for consumer. So it's a pair of glasses, correct? If we speak about this, so I like to say to people, the first thing when you buy a pair of glasses is first of all a fashion accessory. I mean, first of all, it's to see well. It's a fashion accessory, and then if you can do something else.
Mm-hmm.
So our form factor is fixed, correct? It has to be here. It has to be comfortable. You have to see well, and you have to look nice.
You don't have your Ray-Bans now, as I see. That are your usual
I
glasses.
don't have Ray-Ban. I don't have Ray-Ban. This is a French blonde.
In the same respect, if we're speaking already about the devices themselves, do you believe that, or you may also be very careful in addressing this question? Do you see, or is it a perception that the Google will continue this path rather as a software supporter or also as a hardware developer? Because of course you know all about hardware technologies, but do you rather concentrate on providing the operating platform for all of them, or do you also eye your own products? I'm a proud owner of Pixel. That's why I'm asking.
Great, great. I also have Pixel. It's a wonderful phone. I cannot comment on this question.
Okay. Thank you so much. If there are no further questions, I think that's not the case. Maybe I would like to introduce you already to the speaker that potentially can help you the problem to address the problem of further miniaturizing the light engines. And this is Tin Konginovich from Nexus Photonics. Tin, are you here with us? Please unmute yourself, switch on camera, and tell us about Nexus Photonics and what you can offer for the next generation of XR.
Thank you, Olga. Very excited to be here. So my name is Tin Konginovich. I'm the CEO of Nexus Photonics. And Nexus mission is essentially to power the future with photonic integrated circuits. And the way we do that is that we are trying to essentially make PICs same as electronics. The goal is to make a fully integrated system on a chip in wafer scale. That means that it has on-chip sources, other components, and then you can fabricate, test, and singulate at wafer scale. And where we differentiate from maybe some others, we really support broad wavelength range of operation. So what you can see here is automated wafer testing of a blue source, a red source, something more like sensing 940, and then of course long wavelength source. And so with this in mind, we're going to show you a glimpse of what we've been developing. Obviously, maybe our focus here is on displays, and we can talk about that. But here, what we're going to show you is the platform that actually supports 3D depth perception. To kind of give you a heads up, I'll first start with a video because it might capture your attention. So basically, these are Nexus eyes that we made for the upcoming Halloween, and the purpose is to track who's taking the most candy. But because it's movable and you can see, it's a 3D object, we use that to show you how our fringe illuminator can help you detect depth. The benefit of making things in our platform is, one, they're the smallest possible. Below, you can see an example of the size. And I think that's crucial once you think about wearables. In the same fashion, everything else that you build in our platform is of that size because the chip is fully integrated. There's no packaging around it. For this particular case, we are showcasing fringe illuminators. And, the nice thing about the platform, it really is a customer customizable component. And here we're just listing, high-level, publicly available specs that you could design the component with. You can design a field of view. Maybe you want it very wide if you're close. In some cases, you might want it to be more narrow and have better power efficiency. That's all possible. You can do various wavelengths. For these things, you probably don't want to go down to blue. Even 650 is too short. 940 is probably ideal. But we wanted to highlight it. You can tailor it to multiple wavelength regions. And of course, you can change fringe densities. You can actually have multiple fringe densities on a chip. One thing that we'll not disclose publicly, but if you're interested, I think this platform enables significantly superior optical performance because we can integrate various types of lasers. So, we are orders of magnitude better than LED lighting that's so broad and you can see the glow, but we're also better than VCSELs, both in terms of wavelength stability or single mode output power. The fringes can actually be steerable. We're not showing it publicly here, but reach out if you're interested. And that can actually give you almost infinite precision if you have some time for acquiring images. Of course, they can be stepped in a sequence or they're like phase shifts, but the continuous steering is really powerful. At the same time, it's super easy to add flood illuminator with no change of size. So that can replace a flood illuminator that you might already be using for, infrared or low light conditions. And it's a PIC, there is an on-chip power photodetector, and you can very easily do adaptive light power management, both to optimizing power consumption, but also for safety. Super small, as said before. And then I think the key, and that key kind of propagates across all of our platform and all the products that we're building, that it's all scalable. The key is it's made on a silicon wafer, it's wafer scale fabrication, it's an encapsulated product, meaning there's 3.5 is not exposed. So you can use basic non-hermetic packaging, super low cost. And as seen before, you can screen and singulate on wafer scale using silicon infrastructure. So we're super excited. We are fully aligned with the goal of making smallest possible components with highest wall plug efficiencies, which is necessary for any wearable. I'll stop here and really looking forward to any questions. And if this is of interest, feel free to reach out. You have my email on the bottom left. Thank you for your attention.
Thank you, Tin. There's quite now some work involved. I mean, there's now the group of the IR Alliance, which Christoph is very much aware, who is now meeting currently, more or less this week, in Denver to discuss the laser backlit ALCOs. You know that the light engine solution based on the laser light illumination in ALCOs displays. Would you say that this technology helps them to address this? Are you able to realize RGB?
In a very early R&D stage, for sure, there is substantial cost needed to scale it at scale. And, I think one thing that we would really like, and, obviously it's maybe too public here, is, what are the through timeline intercepts for a product to align everything? Because, realistically, this technology needs volume. So we are really good if someone's going to be buying 40 million units, but we're not that good if someone's going to be buying hundreds, which you can probably do with assembly. This is all about scaling integration and, towards hundreds of millions. So we're very interested. Actually, wasn't aware. So I'll follow up with you, Olga, afterwards for more info.
Yes, I'll introduce you. I think you will be very relevant for the community. I mean, Christoph can introduce you. He's here. He's the even better contact than I am for this. Christoph, would you have a comment? Do you think it aligns well with the group that working on the laser light engines?
Yeah, I think it was to connect TIN with the AR Alliance.
Sure. Thank you so much. Tin, I have a question because it's all, it's a wafer-based solution. And of course, when you pack so many components so tightly together, there starts to be questions of the heat dissipation and the long-term resistance and stability of this thing. I mean, alignment precision is probably not that critical here. How do you address this?
Excellent question. some of these things are kind of to discuss maybe under NDAs, but we also make things for quantum, which care way more about stability, and we can meet quantum specs. So I don't think, here, I think the most of the issue on the display side is actually wall plug efficiency and size. And so, we can now make PICs with multiple lasers, multiple amplifiers that are all stabilized down to the level of, frequency stability needed for quantum. So I don't think that's an issue, but it's obviously a very complex optimization problem. And kind of how we see this evolving, we don't think that a reference design is going to work. Reference design is only going to show how it could work. Everything has to be fully designed for a particular product, I think, just to fit the form factor, size and other parameters. But excellent question. On the sensing side, I think that helps it's pulsed. On the display, it could be different because display could be on for a long, long time.
Mm-hmm. Thank you. Any challenges with the production that you would like to address, or maybe a call for collaboration? As Christoph started, we all want to do it together. Would you imagine that you need help from the other Optica members to address some of your own challenges?
100%. We were basically, deep stealth building our platform. We're now kind of showing a little bit more. And, I think we're trying to use the opportunity to show people what we've been up to. And we would definitely want to get feedback from anyone who sees interest, because it's all about alignment and synergies and building the whole ecosystem, as others have said before as well.
Okay, thank you so much. Any questions from the auditorium? My colleague John Pugh. John, do we have questions?
Nothing currently, Olga. Nothing in YouTube either.
Did something interest you as the person from Quantum?
Yes, absolutely. I'd love to talk to Team further about his work in quantum and the collaborations he has there. Obviously, we have the summit coming up next week, so please do come and discuss with the quantum companies.
Well, then I will use an opportunity to actually potentially introduce the next partner, and Tin, you can probably even work together with our next speaker, is Ron Timmerick from Vitria Lab, and also a part of the IR Alliance, and we currently already have any collaboration for developing the light engines based on the laser illumination. So I think the more partners are into the game, the more interesting it is. Ronnie, welcome. Tell us what you do and how you can help, or let's say, what's your solution for the XR world?
Thank you, Olga. Thank you for the introduction. Yeah, so my name is Ronnie Timmerick. I'm the CEO of Vitria Lab. And of course, we can also contribute, I think, a lot. So because we want to make true augmented reality a reality. And that means that AR is the objective that feels really natural, as if you do not have any glasses on your head. And by the way, this also answers the question many are asking. So they're asking, you're working on AR glasses, so why aren't you showing glasses on the head of your key visual? Yeah, because this is the objective. So AR glasses that are so lightweight and immersive that they seamlessly integrate with you, so your surrounding and the digital world. So feeling completely natural. So of course, we are only working on the display part of the glasses. So there are many others who have to do their homework, other technologies they need to develop. But with our tiny little projector we are working on, we have already done a part of the homework. So let us go through the requirements that the industry gives us. And Christoph already has told a few things about that. I want to dig a little bit into detail. What we got as requirements from the industry to build glasses, to build the display part, or especially the projector, because we are focusing on the projector. So here's a kind of list. Also ordered in terms of the priority we got. So the first thing is size. Of course, everyone wants a small thing, not a helmet-like device. That's quite clear, to be really a tiny little device that's not feeling like a big thing on the head. It need to be small. 1 cc is the goal for the projector. So we are talking about this tiny little thing here that's integrated in the temple of the glasses. So not the combiner, because we have to combine with the combiner, but we are doing the projector. So 1 cc is the objective for this. You want to use that at daylight. That means the brightness need to be in the range of 10 lumens. So the numbers I give here are just kind of ballpark numbers, as they are also, of course, interact with each other. Though if you want to have a huge field of view, you also need more brightness, but 10 lumens is a good value. Efficiency, very important, because nobody wants to have a device that drains the battery empty within an hour or so. So 10 lumen per watt is a value necessary to achieve. High quality image is of course a must. So the people are today they are used to iPhones, to Samsung phones with a super high image quality. This is what they also expect from the glasses, and of course a super large field of view. The step that Meta did is great with 20. That's the first product, but of course 50 or even 70-degree field of view is necessary for real immersive images. That's why this is also a requirement of the industry, and it needs to be scalable and low cost. Olga, you mentioned that. It's very important. So no OEM will integrate a technology that costs, I don't know, $100 or so in the bill of material. So the display part can probably be all in all in a range of probably $200 even, but for the projector, there are certain limitations, and this is our solution for that. We kind of combine the best of two worlds. We take the laser, which is the brightest light source you can imagine, and the LCOS, which is Christoph already elaborated on that. It's a mature technology, and combining that together, we can make use of both advantages. So in the end, what you can see here is a tiny little explosion diagram of a example projector that we can build out of our technology. So what is our core technology is also called quantum light chip. This is a photonic integrated circuit that can manipulate laser lights in 3 dimensions on a micro scale. That means we write a waveguide structure in that glass that enables us to split laser beams into many beams, redirect them, and in the end, we can produce an array of laser beams out of that. And with this array of laser beams, we illuminate the LCOS. And that gives us the advantage of both of the two worlds. We have the super high brightness of the laser. We have the efficiency. The overall efficiency of the system is much higher than of a LED system, and we have the image quality and the efficiency of the LCOS. By the way, the LCOS isn't limiting the efficiency in typical systems today. It's only the illumination. And we can, by the way, with the laser, even increase the efficiency of the LCOS. For some details I don't want to elaborate on. And that's the way we can really achieve the mentioned 5 requirements, because this is key. If you want to be successful with such a product, you need to fulfill all 5 criteria, all 5 requirements at the same time. And this is exactly what the other technologies that are already in some kind of products cannot do. And therefore, we only have the 20-degree field of view in the Meta glasses. And we do not have an real immersive product yet. And that's exactly what we are aiming at VitraLab, to get glasses that look like here on the slide, with a tiny little projector integrated in the temple of the glasses.
Thank you, Ronnie. Can you elaborate a little bit, maybe if you can, on your partnership with Brilliance, who actually provides the laser sources, peak-based laser sources?
Yeah, of course. So there's one challenge with our PIC. We have this technology of the waveguide structure in the glass, where we redirect the light, the laser beams. But of course, we have to couple the laser diodes to that PIC. And this is exactly where we are collaborating with Brilliance, because that's what they do perfectly. They can couple the laser diodes in a very, very simple process, a very efficient process to into a PIC, and that's the field we are elaborating. We have different solutions for laser diode coupling, but Brilliance is, I would say, the most efficient technology we are currently elaborating on.
With which materials is your technology compatible? Because now there's, as Christoph already mentioned, there's quite some interest in silicon carbide, and not only for the waveguide solutions, but generally for the optics within the XR systems. are you compatible with the selection of different materials, or should it be something strictly particular?
Yeah, so the one strong advantage of the technology is it's super simple. What we do is we take a piece of glass. It's just display glass. It's simple display glass. So that tiny little thing that you can see here, where the laser beam array comes out, is display glass with inscribed fibers. So with a high power laser, with a femtosecond laser, we inscribe fibers into glass. So there is no need for silicon carbide or anything like this. It's a really simple piece of glass. Of course, we need to couple the laser diodes. We have mentioned how we can do that. And of course, we have to do a package around it. But that's it. And this is also a scalable process, by the way. This is, in the end, in that light engine, it will be the least part of the bill of material.
Mm-hmm. Thank you very much. I will turn to the public if we have any questions or comments, or maybe even from the speakers themselves. Christoph, Tin, would you have a comments or questions to Ronnie?
I have a quick question. Thank you, Ronnie. What is your biggest challenge right now?
The biggest challenge is to bring that into a product. So we are currently in several projects with OEMs and with ODMs already, and defining the very first product. This is currently the challenge. So building up or defining the specifications of that product and developing this into a producible product.
Mm-hmm. Ronnie, also maybe another question, because I know that you can use this technology the other way around to increase the efficiency of basically CMOS sensors. So if you can imagine stacking several of your plates which are guiding light to the basically distributing it into the CMOS sensor, you can increase its sensitivity. Not sensitivity, but the total amount of light that reaches the sensor, and thus improve the image quality. Have you thought about it?
Not really. So of course we have some other applications that are also potentially addressable with this technology, but we are currently focusing fully on augmented reality because this is really product market fit for the technology, and the technology has been around for already six years. So the team has done a great job in building this projector out of it. So the other applications are on our radar, but we are not focusing on them currently.
All right, thank you. And as all this time I was observing our next speaker, Hanan Shamir from Everyside, and looking at his reactions. Hanan, what are your comments right away to the previous speakers?
I believe that this is a very promising approach. Obviously, it's very, very interesting. One thing that I would like to ask is about safety, because lasers are involved. Did you have any analysis or any approach to keep the safety intact?
Yeah, it's completely eye safe. So we've done our homework on that with simulations and calculations and measurements. So because we split the lasers into many beams, there is there's no danger of getting any critical intensity into the eye.
And I guess also no significant heat accumulation, because this thing sits next to your face. You also don't want it to be hot.
Yeah, no, the efficiency is higher. So if you compare this to an LED illumination, the efficiency is higher. And that means we have less heat dissipating in the overall device.
Okay, thank you so much. Hanan, thank you for the comments. And then I would like to use the opportunity to actually give the floor to you. And to really come to the real life devices in the form factor of the glasses that Christoph so interested about. Please, the floor and attention everyone is yours.
Excellent. Thank you very much. Thank you for hosting us. Again, my name is Hanan Shamir, co-founder and CTO at Everyside. And today we are going to speak about mobile AI, enhancing the intelligence with gaze. Going on, starting with the first model that we have, the Maverick 1. which is actually for more than a year now in a mass production stage. In this model, obviously, as you can see in the pictures, its style is more tending to sports performance DNA. You can see here that we are using a full color OLED display. So in our case, the efficiency of the optics itself allows us to use an OLED display. Here in this Maverick 1 is a 22 degrees field of view. That is sufficient to compete against the sun for a fully sunny day. And actually, the power that we have allow us to work for 10 hours continuously, where the display is always on, connected either to your smartphone or to your watch. And this is all encapsulated into less than 43 grams. The solution also incorporates an interchangeable prescription lenses. Here you can see on the left that we have a very good collaboration with the BMW Motorrad, where they are actually selling our product under their brand. Obviously, you can see here that they adapted the model, but they tweaked the CMF, the color material finish to their definition. So we did that already. On the right side, you can see our own Maverick 1 that we are selling under Eversight brand. Moving on, our next generation, which we are working on that for more than a year now, is to move from the Maverick 1 into what we call Maverick 2, which is an AI glasses. In this case, you can see that we actually tweaked the design to be more attending the active lifestyle DNA. Again, we have a full color OLED display with a field of view of up to 28 degrees. Our optics is very, very efficient, meaning that we are able, again, to work at the full sunlight. The resolution is a retinal level resolution. In here, we have the ability to work more than 8 hours of continuous operation. Again, when we say continuous operation, where the display is always on, and we are connected to the AI. In this case, our weight is less than 47 grams. Again, interchangeable prescription lenses, no inserts, meaning that the lenses that you see here are interchangeable. The user can switch the lenses. And we are launching that in the upcoming CES, which will, the actual glasses will be available mid-26. In the next slides, I'm going to concentrate on prescription lenses and eye tracking functionalities. Here you can see all the rest of the components spread around this model that you see here. So starting with a prescription, our beam technology, beam optics, allow us to integrate the ophthalmic prescription into the lens itself, meaning that our technology allows us to leverage, to utilize the front and rear lens surfaces to tweak them in order to change and adjust the power. The way that it's done is that by tweaking the rear surface, allow us to correct for the display focus to the user prescription, and the front versus the rear, actually those two curvatures play together in order to correct for the power of the see-through vision. For that, we implement the surface coatings, meaning that on front surface, we implement the anti-reflection coating, and in the rear, we implement a semi-transparent mirror, either on the vis spectrum or for the option of integrating the eye tracking, we are coating that with the vis near spectrum. Now, the benefits for that approach is that actually we build the prescription into the lens itself. So it's a minimal weight addition, only tweaking the rear and front surfaces, curvatures. We are agnostics to the visor color, meaning that we support both clear, tint, photochromic, color, whatever, gradient colors, and whatever you can imagine, like what you probably see in any sunglasses or ophthalmic glasses that you find out there. The user replaceable visor allows seamless prescription updates, meaning you can appreciate that people change their prescription maybe between 1 year to the next, or even during the years. So just imagine the hassle of integrating something which involve waveguide and involve the display. It's a hassle and it's a costly issue. And here you just switch, click off, click on the next lens, and you switch the power by itself. We support, as you can see here on the schematic, you can see that we can support a progressive multifocal prescription, which is very important, you know, when you would like both see far away, also the display, and when you lower your eye downwards, you can see your watch or whatever you would like to read from close proximity. And we are using the same material and the same manufacturing process as regular ophthalmic are using right now, the industry. The main challenges that we are facing, obviously, we wanted to share here are regular power, meaning that for regular power, we need to maintain surface integrity over a large area. You can appreciate that here, if we are using, you know, the glasses for multiple in-action activities, it might be that for certain portion of the day, you would like to use with the upper loop when you actually lean to your bikes or looking up or doing some extreme, you know, performance, or when you just sitting down and lower your eyes downward, you will look through the visors, I would say, from a different angle. So then you need to maintain the integrity over the large area of the visor of the lenses. In another issue that we are challenging is the progressive power, which here we need to polish the front surface with free-form shape, and this is another challenge that we are facing, and this is a very interesting point from our side. Moving to the eye tracking, again, the beam optics, here you can see that we leverage two portions of the beam optics. One is that we are using actually a dual spectrum approach, dual spectrum operation, and a bidirectional operation, meaning that we operate in the visible for the display and in the near-infrared spectra for the eye tracking. And in conjunction, we are projecting the display forward towards the eye where it is being reflected from the visor. And in conjunction, we are doing that in a reverse direction for the tracking path, meaning that we collect into the camera the near-infrared beam, which is reflected from the face, from the eye itself. The key advantages for that is that we are agnostics to visors, color. It doesn't matter which color it comes with, whether it's clear or tint, it still works. We preserve the visor replaceability by the user itself. We support embedded ophthalmic power, which we talked about in the previous slide. Again, it is preserved also for the functionality of the eye tracking. We support a coexistence with automotive ADAS systems. So in the case of our system, we operate in 850 nanometer band, which ADAS works at 940. So in our case, we are actually transparent for ADAS. ADAS still can see our eyes without interfere, and still we can work inside with the eye tracking seamlessly. We have a high optical efficiency, maintaining low power consumption, and we meet all radiation safety standards. The main challenges here are, like I presume that most of the companies that are dealing with eye tracking is eyelashes, eyelids, obscuration. We need to deal with that. Stray rays from sunlight. Again, if the glasses are outdoor, obviously we will face some stray rays from the sun. Assembly and alignment. We are dealing with a very tiny components, kind of the camera and the illumination. LEDs are very tiny, and the harmonization of those and the alignment of those making some challenges that we need to face during the assembly. And we are using a neural network processing, so the model size is very important in order to preserve both size and power consumption slow and to be encapsulated into the frame of the glasses. Just a quick demonstration how it works. I hope that the video works fine. So
it works well.
So here you can see me wearing the glasses, and simultaneously you see over the phone how it's being collected from the phone. Actually, it's not tethered by wire rather than by Bluetooth low energy, which our system works with that manner in order to leverage the processing power of the connected phone. So here you can see how we actually analyze the eye features in real time. Okay, so obviously you can see here both the pupil, the iris, the eyelids, corners, the corneal reflection, and the gaze angle are being analyzed. And we just show that how it's been analyzed by the system under the hood, I would say, using the phone itself. So this is the way that it works. Moving to the application level. So here you can see the applications that we are dealing with once we have the eye gaze angles and features. So starting from the left, starting from the eye features, we are experimenting and evaluating how we can measure the cognitive state, I would say, or the emotional, the excitement state of the person who uses the eye tracking in conjunction, of course, with other telemetries. I would say that we can measure kind of heart rate beats from the watch or EEG or something like that. So in order just to understand the excitement level, I would call of the user. So it's very interesting for us. Another portion that we are doing is that in the middle you see that the interaction between the display, the line of sight, our glasses obviously have the line of sight, and the gaze angle, the eye gaze. So in the combination of the three, we can leverage in order to manipulate the user interface. We can actually manipulate the load of the graphics in front of the user. We can actually do all of those in a most efficient way without any other interactions and in a very private manner, and optimize that to the real-time operation of the user, the intent of the user. And on the right side, you can see that obviously once we have, as you saw probably in the slide that is dealing with the Mavic 2 AI glasses, we also encapsulate a front-looking camera for AI. So the interaction between the camera, the line of sight, and the eye gaze allow us to pick, those objects of interest to the person who wears the glasses by knowing the line of gaze, exactly where the eye is looking within the field of view of the camera. So that allows us in a very convenient and intuitive way to understand the intent of the user at real time. So obviously here, the challenge is how to preserve the power consumption and the size, the weight, and like Christoph was mentioning, the style comes first. So everything needs to wait at the certain, at below the limits. Should be a sufficient time to work both indoor and outdoor, and to be encapsulated in a fashion way that people won't be embarrassed to go outside with. The last thing is that we will be at CES, at the upcoming CES, and we invite you to meet us and experience yourself, the Maverick 2, both with Maverick 1, obviously. Thank
I
you.
would love to stop by. Thank you so much. Hanan, why did you question right away, why did you decide for OLED? OLED display.
Okay, again, excellent. We actually, at the beginning, we were using, LCOS and and even laser scanning and everything. But eventually we understood that in order to gain most of the ability to work for extending for long time outdoor, you need to start from the beginning. You need to make the optics as efficient as possible in order to use those technologies which are the most fitted for outdoor, for AR usage. And OLED are excellent. Keep in mind that OLED, the contrast is excellent, but the deficiency of OLEDs is that they cannot deliver the high energies or the high brightness as micro LEDs or LCOS, okay, obviously. So in order to use OLEDs, which are mature technology, but up to 10,000 nits, you need to start with the optics. And in our case, the optics is around 20% to 30% efficient. So let's say 20% of the brightness of the OLED is coming right to the eye because it's a free space, off-axis, traditional optics that everybody knows. And here the challenge was to squeeze everything to the size of the glasses while maintaining everything else as people expect, the field of view, everything.
Christoph, you had a comment, a question. Go ahead.
Yeah, thank you. Thank you, Hanan. This is a great presentation. Can you comment on the size of your eye box?
Yeah, the size of the eye box, we actually picked that to be 6x4 mm, okay? And actually we have the Maverick 2 made in two sizes. So Maverick 1 and Maverick 2. So we have a medium size and a large size where we cover the full population. I think that it's about 99% of population that we cover. So people pick their own size, whether it's medium or large, and the iBox supports all of them. Keep in mind another thing, Christoph, very important thing. Once you switch to ophthalmic, okay, the regulation of the standard for using ophthalmic is a 5x5 mm. You need to precise to bring the iBox of the ophthalmic solution to exactly be allocated in front of your eyes to 5x5 mm. This is the regulation for ophthalmic. So what is the point of doing, a large eye box, let's say 10x10 mm, if you want to include an ophthalmic, and then you need to, adjust the full solution up to the point of 5x5. So we understood that, and along with the energy efficiency, in order to preserve as much as energy efficiency to the eye. So that is why we picked 6x4 in order to support that.
Thank you.
Thank you. Christoph, you happy with an answer? Christoph,
Yeah.
you happy with an answer? Yes?
Yeah,
Good.
Thank you.
I have also, Hanan, you mentioned that you know that you basically click on a different lens. And I would like to ask maybe a couple of details. Is it somehow passive alignment? How does it work? Because aligning the light engine to the waveguide is usually an issue, that you have really a proper image, that your colors are homogeneous. What's the trick there, if you can share?
No, the answer is very, very simple. We are using a conventional optics like you are using, in any traditional optics, no surprises, no things. So the alignment is, the tolerances are very, very rough. Even I would say I can disclose that when we assemble the optics itself, it's a drop-in. We are not doing any adjustment during the assembly process. We just drop all the elements one after the other, and the only calibration is done by the end of the process, just determining the distance of focal. In our case, it's not fixed to infinity. In our case, we fix that either to infinity, but most of our customers requires that to be 4 meters, between 2 to 4 meters. So we adjust that, and this is the only calibration that we are doing within the process. So again, the tolerances are so loose, so we can actually switch on, switch off, and click that very easily.
User-friendly solution.
Yes, exactly.
We actually have, so we're also live stream on the YouTube, and we have questions from YouTube. And I'll call my colleague John Pugh to raise these questions. John?
Yes, Hanan, firstly, congratulations on achieving great technology with something that looks really aesthetically pleasing. But there's a question on the lenses from YouTube on what's the highest and lowest lens powers supported by your system for spherical and cylindrical corrections?
So currently, what we are providing, you can see that between -3 to +3, okay, diopters. This is what we provide, and the cylinder is up to -1 diopter, okay. We actually, in certain cases, we provide more than that, but it's more effort. So I would say that what I said before is something that we definitely commit for.
Thank you.
Thank you.
John, further questions?
Not at this time, Olga. Back to you.
Then back to Munich and back to next speaker. Thank you so much, Hanan. And I would like to also, now we're slowly moving from discussing light engines and a little bit of the, let's say, on all the optics inside, more to the other part of the XR experience and XR sets, which are the waveguides. And in this respect, I would like to actually introduce a couple of our speakers that are actually very active in this field. And I will start with introducing to the floor Marco Abarchi. Marco, I apologize if I pronounce your last name wrong, from Solnin, and the company which develops actually functional materials for creating creating the waveguides or improving the efficiency of those. Marco, however, the floor is yours. Marco, we don't hear you. Okay, then let's give Marco an opportunity to fix the technical problem. And then I would like to introduce Kelsey Woolley from Ulitha. And Ulitha is the company which develops equipment for producing high quality waveguides. I mean, many products, but especially waveguides via the lithography methods. Kelsey, you're with us from the wonderful Denver.
Yes, yes. Can you hear me and see my screen all right?
Yes,
All right.
we can hear you and see you. Please introduce your Letha and how you address the challenges of the XR world.
Yes, thank you. So yes, like Olga said, my name is Kelsey Woolley. If you have any questions throughout or at the end, feel free to contact me and I'd love to help you. Ulitha is first and foremost a lithography equipment provider. We sell lithography tools. But specifically for augmented reality waveguides, our solution is particularly interesting and particularly applicable, especially when customers are looking to go from research scale all the way up to high volume manufacturing and integration into existing infrastructure with their foundries or facilities that they're building out themselves. So Ulitha is a optical lithography, which means it most closely resembles projection lithography, where you have a laser source, you have a photomask, and you image on photoresist to create a mask. Our tools are very similar to projection lithography in that sense. What is a little bit different is the cost and the complexity of our tools. Our imaging is a little bit different than projection lithography in that we use the mask a little bit differently. What this translates to is that we're able to provide customers with the same performance specs and reliability and essentially image for a fraction of the cost of buying a full projection system at the resolution that's needed for augmented reality waveguides. So that's typically in the DUV range, where you have a source that's 193 nanometers. So of course we have tools that match that as well. So there's some SEM images here of what that can look like. The limitations of our tools are that it must be periodic structures. There has to be symmetry to them. So this is why the AR market is such an interesting one for us, and one that's been growing so fast for us recently. So that is one of the things that we bring to the table is when customers are looking to scale, and yield is very important, and they need to integrate into their foundries. Optical lithography is a very mature, very robust approach, and that we're able to provide optical lithography for the same specs at a fraction of the price, which is so important when you're printing augmented reality waveguides, where cost is so important to the final device of what you're final printing. So being able to offer lower cost options for our customers is the specialty that we bring to the table. Other things that we do very well is because we do not have reduction or magnification optics like projection lithography has, for example, our exposure fields are very large. They're the size of the mask. They're actually mask limited. But what that translates to for folks looking to print waveguides is you're able to print multiple waveguides in a single exposure. That means all of the waveguides that are printed within about a 6-inch area are seamlessly and exactly printed. So this is really excellent for having very, very accurate pitch, K-vector control, anything. It's very nice for designers to have that accuracy. So you don't have to stitch anything together. There are no stitch fields in your waveguides. So just to reiterate the introduction of our company, we specialize in the equipment, but we also specialize in working with our customers. Almost all of our customers come to us with what they're looking for, what they ideally would like, and we help them develop the solution, and we help them plug in our solution into wherever they're at in their manufacturing process. So we're used to having a very tight partnership, a very advantageous partnership with our customers, where we're able to provide our expertise to ensure that their product is as successful as possible.
Thank you. And you also opened an application lab in your headquarters in Zurich, correct? What are you able to offer there?
That's right. So we actually have an expanded demonstration lab in our headquarters. We have our tools there. We have metrology equipment. We have some support etch equipment. Basically anything to do those demonstrations or small volume production runs, depending on what customers are needed. We're able to support a fairly decent volume out of our headquarters lab. We also have a brand new demonstration lab that opened last year in Beijing. So this is really important for our customers where that location's important. So whether you're in China or close to China, that Beijing location means we can get wafers in and out a whole lot faster. People can come visit and see the tool. We can teach people on the tool. We can do a lot from that secondary demonstration lab as well.
Thank you so much, Kelsey. Any questions for the speaker from Yulita? Comments? We actually had a very interesting comment in the chat that I would like to raise and maybe invite the person from Daniel Gomez Tejada. First time in IRVR meeting. Daniel, are you here? Maybe unmute yourself? Maybe not. Well, anyways, first time the IRVR meeting, the hot optical engineer just realizing how much concepts has in common both technologies with the head-up displays and IRVR. These are very similar tech.
Daniel's completely correct. So we sell a lot to the heads-up display folks as well, because all of the advantages of the large area, high resolution, very accurate printing for low cost translate directly to heads-up display too. So for heads-up displays, typically they're larger than 6 inches, and we can do step and repeat. But when it comes to like a diffractive heads-up display and a diffractive AR waveguide, there's very similar principles and very similar types of structures that you're trying to print on your wafer.
How about
Olga.
your yes?
Sorry, I have a quick question.
Go ahead, John.
Sorry. Kelsey, I had the pleasure a few years ago of working with a Fable machine with the University of Bath, and they created what they called double displacement Talbot lithography. So they moved the pattern of the mask as it was exposing the normal exposure through the Talbot length using the Fable. Have you found any application for that in AR VR, or can you see any application for that?
What was the intended effect on the pattern?
So they could move the actual mask pattern so that it didn't need to be a sort of linear grating. They could move it during exposure.
Oh, I see. Yeah, there isn't direct overlap at the moment. The way that we go about the patterns that we make for AR, we do in a way that's very, very reproducible. Mask movement introduces some mechanical engineering concerns for repeatability and scale. So the way that we've gone about it so far is making sure that everything is very reliable, repeatable, and therefore mask movement hasn't been something that's been needed for AR yet.
Thanks.
We have a question in the chat from Mark Brennan. Mark, please unmute yourself and ask your question to Kelsey.
Hi there.
Mark?
Yeah, no, thanks for your... Hi, can you hear me all right?
Yes.
Yeah, okay.
We did cute.
Good.
Now, happy to see you here.
Yeah, thank you very much. Yeah, thanks for your talk. I was just having a look at your website in the background. So it's nice to see that there's a sort of desktop version as well. But as far as I can see from all the examples, everything looks binary. But then I guess what John was alluding to, if you can move the mask during it, are you able to raster and produce like blazed gratings or any kind of like 3D structure?
Yeah, that is a great question. For the tools that we have currently as available for customers and the high volume, it's all binary. Everything in semiconductors built around photolithography, providing a binary mask that again goes to etch. That's kind of the mature standard manufacturing process. Three-dimensional is of course interesting to us because that's something that the AR industry is very interested in. The answer currently is no currently. However, there's been a lot of interesting research that we're looking into. Something that's not quite blazed, but might be interesting is we are able to do gray tone lithography. where we're able to do variable resist height, which is sometimes very interesting for AR customers to be able to do. So not blazed, but three-dimensional in a different sense.
Do you have any idea what the kind of bit depth is of that like staircase then, or?
Depth, like the resolution?
Yeah, you said you could do a sort of grayscale type. How many steps is that? Is it 4 bits or 8 bits, or how many levels of gray can you have?
So it's more material limited than us. If you want more details, hit me up after the meeting, and I can share some things with you. But for everybody, that's a materials question typically, because the lithography has a high enough resolution, right? We can print the gradings themselves, but that relationship between now what's the resolution of the litho to what the materials can actually hold from a gray toned perspective is the answer to that question.
Thank you so much. Thank you, Mark Brannan. Mark, also for asking, and make sure to keep in touch after the meeting. So I have to say that actually two of our speakers have technical issues, so we will change a little bit the program. Marco, it works. So I hope technical issue.
Can you hear me?
Yes. Shall we progress the slides for you?
Can you hear me?
Yes, we hear you.
Can you see my slides?
Yes. So please go on.
Okay. Okay, thank you very much. Today I'm representing Solnil, a small startup in the south of France, and I'm going to introduce two materials, air coat and high refractive index coat. These are inorganic materials with extreme performances adapted to augmented reality and photonic metasurfaces at large. The first product is air coat, is basically silicon dioxide, and the other product is high refractive index is titanium dioxide with high refractive index. The second product can be used to directly print three-dimensional nanostructures such as slanted gratings or metal lenses or photonic metasurfaces in general. And the first product, the low refractive index, can be used to encapsulate. Basically, you need to protect this delicate and tiny structure from humidity, dust, etc. So you need something to overcoat this 3D structure. So you have, by one side, a product which is titania that is printable with high resolution, and the other side, you have a very low refractive index that can cover it. And what you see on the right, this ultra low refractive index can be used to stack metasurfaces one on top of the other, which is a bit the frontier of photonic metasurfaces, to couple different metasurfaces to add functionalities. So these two materials have 1.12 refractive index with exceptionally good optical quality, so extremely low absorption and scattering and very, very low haze. And the second one, the high refractive index coat, has a refractive index of up to 2.6 and very low scattering and haze. These materials have been assessed against many properties: thermal shocks, humidity, water repellence, UV resistance, adhesion, dicing, and chemical resistance against acids and solvents, and have been all passed through. And so these products are basically ready to be shipped, to be integrated in your production line. Very important, the last comment that I want to leave you with is that these materials are obtained from liquid solutions. They can be spin coated with a conventional spin coater and stabilized by annealing, by curing. So you don't need very expensive ultra-high vacuum processes that can be eventually very expensive and slow. And with this, I thank you for your attention.
Thank you, Marco. How about, what are you mentioned already spin coating, any other manufacturing processes you're compatible with, your materials are compatible with?
The other way is deep coating. So, for example, you can take a wafer and dip it in the solution, and by removing it, you can adjust the thickness depending on the speed. So this is another good option that we are using, and yeah.
And how about shrinkage? You know, it's very often an issue for the materials that are polymer based.
For the very low refractive index, I don't have this number, but my educated guess must be around 30% in volume. For the very high refractive index, the retraction can be much, much larger. In volume can be about 70%. So we are working around this. For example, you can use the same material to fill nano cavities. So you work with a nano pattern in glass, for example, and you can overcoat with a high refractive index so that you are not limited by the retraction, the volume loss.
Okay, there is a question from Christoph. Christoph, here we go.
Thank you, Marco. A quick question: what are your post-processing condition for this low index? Do you need annealing, or how do you process the material after coating?
Marco?
Lost any connection. I can't hear. I'm sorry. Can you repeat the question?
No, my question was,
the question?
do you have any post-processing condition for the low index? Do you need annealing, UV? After, what do you do?
You can annealing. It depends on the substrate. You can work at 450 Celsius. For 5 minutes, you get the final product. If your constraints are...
I think I will introduce you later because Mark, the connection is really horrible. Mark, I will introduce you later. And then there was another question to you from Incron.
Higher.
Yes.
You have, I mean that you have this, and then compromise. High annealing, short time. Low. Yes, you can cure at 40, or you can anneal at 250 Celsius for 5 minutes, for 40 minutes, sorry.
I think I will introduce you later because it was really, maybe write this in the chat. That will be the easiest, exactly. Thank you so much. Just, Christoph, your question will be also answered in the chat. And you also had a question from Incron, Honda Karim. Also, please address it in the chat, okay? Thank you. All right, and meanwhile, one of our speakers still has technical issues, and that's why I would still prefer to move on smoothly to the speaker from Heteromerge to present their solutions for the XR world. Joshua, tell us what you have and what you can put on the table as your offer for the IR, VR, and generally XR.
Hello, Olga. Sure. Just trying to find the right monitor here. No, that wasn't it.
I know the issue. I also have quite a few. You need to now to switch to the presenter's view.
Yes, wait a second.
Yes.
I think that's it. Okay. Hello, my name's Joshua. I'm from Heteromerge, the CTO software. Thanks everyone for joining today, and also thanks to the incredible Optica team as always. We are Heteromerge, and we print Optica systems. So what we do is we combine different optical materials in a, wait, can I switch further here? Yeah, okay.
Yes.
We combine different optical materials in a single print process for very compact freeform micro optics. So we are using two-photon polymerization technology, and we elevate their advantages of high precision, for example, with our proprietary multi-material technology, which means we are reaching the highest alignment accuracy between different materials on the market across all printing volumes up to the millimeter range. So we're talking low micrometers up to the millimeter range. The demonstrated examples that you see here, they cover achromatic focusing stacks, as well as imaging optics with included aperture material. And as you might know from 2PP printing, complex multi-stack geometries are possible, and with us it becomes a multi-material solution for highly compact systems integration. We are offering our printing technology, for example, for XR applications, of course, where you require these ultra compact collimation or combiner optics. So I cannot talk about everything concerning this project, but in the current project, we are demonstrating printing near to or even onto the optical engine modules to gain further system compaction and weight reduction. We already heard today that that is, of course, an important factor, the form factor of your XR device and the weight. So this combination of lightweight printed optics and ultra compact optical engines can help to reduce the overall system volume even further than we've seen it today. And the technology is ideal for like our 3D printing technologies, ideal for prototyping, but also we can scale the production up. There are already currently industrial printing systems in the 2PP environment, and there are promising technologies for future speed ups based on massive parallelization. So if you have a challenge to integrate broadband optics more efficiently, we would be very happy to have a talk with you. Thank you.
Thank you, Joshua. A question right away, because for the XR world and generally for the such solution, it's very important to be scalable and to be able to produce in the very high speeds. How can you address this challenge? How your technology couples with it?
Okay, so in general, we are limited by the 2PP printing technology that is on the market. We've already seen in the last years quite a speed increases for the print itself. And obviously, we are introducing also material exchange into the print process, but first of all, in a fully automated step. So all can be done in one machine and in one process. And we are working hard to reduce the material exchange time. And we are currently looking at low minutes of exchange, and we are improving that further.
So would you say really the bottleneck is how quickly you can switch between different materials? So the
No,
less selection in the system you will have, the quicker you can be.
In general, I would say the limitation is really the printing time. That also depends, of course, on your system configuration and the micro object in general that you're trying to print, right? So how high fidelity has your surface to be, for example, limits the printing time. So unless you have very extreme differences in the liquid, so in the resin state, the material exchange is not the limiting factor here.
Thank you. You've seen so many speakers. With whom would you like to work?
So that's a good question, but actually we are basically the engineers making this material exchange and the seamless integration into printers possible, right? So we are not optical designers. We would like people that have an optical design or that have an idea of how an optical design that could be very small. We would like to have these people in general come to us and say, hey, just we have this and that idea. Is that possible with your technology? And then we'd have a talk. So yeah, there's no single one participant today that we would say, hey, you are the right one for us.
Do you have maybe a real life example where you printed something that was not possible to realize with other technologies?
So as you know, next to like we are giving our technology in the form of a printing service, and with most participants there, we sadly have to sign NDAs, so I cannot really comment on that. Sorry.
Okay, thank you so much. Thank you, Joshua. And I would, as the last but not least, I would like to really introduce to the floor the speaker that can contribute to all the possible, to the XR devices, to the XR sets on every step of their development, and waveguides and light engines and optics and everything in between. It's IMAC and Matt Traub. Matt, we're looking forward to see really what you can offer, and I believe you can work with all the speakers of today. Tell us what you have.
Thank you for the very kind introduction. Yeah, so just to give a little bit of a sense of what IMEC is for those not familiar with us, we are a not-for-profit independent R&D hub. We have locations at several points in the world, but our headquarters in Leuven, in Flanders, in Belgium. And that's where we have our main clean rooms at this point. So we don't have to go through all the numbers, but I think the core point is, we have quite a bit of semiconductor fabs. There's new ones under construction, and that includes fabrication capability at 200 millimeters and at 300 millimeters. And when we talk about the industrial partners, that includes essentially the entire patterning ecosystem. So on the lithography end, that's everything from, we have E-beam, but also eyeline tools all the way up to extreme UV, in partnership with strong partnership with ASML in the Netherlands. And then all the other parts of the ecosystem that go with that. So the pattern, the etching, the metrology, the deposition of different materials, and things like CMP, which are often overlooked. And the core thing driving this is, of course, the semiconductor roadmap and transistor scaling. And that's a significant piece of what we do and what we're most known for. But we do work in a lot of other fields. So that includes health, automotive, and various photonic applications, including for consumer or industrial sensing, like in AR or XR. The other thing to note here about our funding is we do get some government funding. We work with public EU funding and got funding from the Flemish government, but about 3/4 of our funding is from partnerships with private companies for development on demand or for low volume manufacturing. So I can't talk about all the technologies at IMEC, but I just wanted to talk about some of the application cases a bit, where we can take the patterning capabilities that we've really developed for semiconductors and look at some use cases that might be interesting. So one is looking at flat optics, where here you can see, I think everyone is quite familiar with metal lenses at this point. And we can do the traditional style that other people have done, quite well, where there's a single layer in a material that's good for the IR, like amorphous silicon, and those can be etched into very high aspect ratio structures with sub-wavelength features. But the other thing you can do is actually with 193 lithography, either dry or immersion, is actually do multiple layers where the alignment between the layers is sub-wavelength. So now you can have these things where you can repeatably use CMP to get very flat surfaces and align these things very well. And that can give you additional degrees of freedom in what you build. So if you want to deal with a broader band source than just a laser, or various other elements you might want to introduce, you now have additional degrees of design freedom. And then by varying the materials, of course, you can go to more complex things and you can start to work at different light wavelengths. So amorphous silicon is nice for the infrared because it's very high refractive index, becomes absorptive at shorter wavelengths. But by going to materials like niobium pentoxide, titanium dioxide, you can start to really access different wavelengths. Now here you see some of the other things we do with this patterning. This is silicon nitride here. So we have a relatively mature silicon nitride platform that is quite mature at 200 and is being developed further at 300, and very low loss silicon nitride. So we can pattern all these traditional structures for PICs. We also, in partnership with IMEC Ghent, in the other side of Brussels from us, we can do heterogeneous integration of laser sources. So things that we can't process in the CMOS line can then be added after, either by another part of IMEC or by external partners if the PIC just wants to be fabricated here. So that means we can take 3-5 materials, things that really can't go in the IMEC clean room, like lithium niobate, can be integrated. So the strength here is that we can do development on demand for concepts that are really done with scaling in mind. We can do low volume manufacturing. depending on the complexity of the structures, will affect how many wafers we can process. And then also we have a lot of foundry partners, so we can take technology and transfer it directly for high volume manufacturing. The other thing I should note here about our relationship with those kind of foundries is that wafers can come the other way. So what I haven't shown here, but that we also do, is imager post-processing. So the same alignment capability that lets you align these multiple layers of a metal lens also means that you can post-process on imager pixels, as long as you come from a fab that's sending out CMOS compatible wafers. So it means you can put things like Fresnel lenses on individual pixels that are optimized for the RGB. You can post-process in polarization elements. So that's also sort of a unique capability that when we just talk about the optics and the display end, there's also the imager end.
Yeah, you have plenty of the unique capabilities. And as this unique research center and covering and nanoelectronics and optics and sensing, how do you bridge, this the gap between really cutting edge research and the prototype development and large scale production? Because as we've heard from Christoph, from Hannah, and from many manufacturers, we need to bring down costs, and that means it has to be large scale.
It's a little bit case by case depending on the TRL that is coming in, of course. We do have one of the things that helps. Again, I talked about the fab lines. We do have a lab that goes up to 6-inch, which is nice because we can do lower cost things, on smaller form factor wafers, but with the processes in mind. So it's done from the start with scalability. So we're not doing something with things like gold that can't go in a CMOS line. We're kind of looking at the process from the beginning. But that said, it doesn't go instantly from a prototype to high volume manufacturing. I mean, there are cycles to reliability is a real concern, yield is a real concern. So doing these on these high end tools really helps you do that, and it also means you probably, if you do things that can go to a high volume foundry, your chances of getting a good price point are better, right? Because you don't have to support your own 183 scanner. You're leveraging the existing infrastructure to keep your costs down.
Thank you. And I'm very much looking forward. Next year, Gamma will take place in Brussels. So I'm very much looking forward to visit your facilities and see with my own eyes what you can do. Well, with this, I would like to close this meeting. Unfortunately, our last speaker did have technical problems and couldn't join, but nevertheless, I'm very thankful for everyone who joined us, to all the speakers, to all the attendees, and to my production team. It's John Pugh, the director for Quantum and PICS, that supports us on everything quantum and integrated. It's Tulsi Patel, who is a great support in terms of the logistics of all these online events, and of course our IT department. Thank you to all very, very much. I have a wonderful closing video, so I would like to share it with you, and I wishing you all a very, very lovely evening. Thank you.
Thank you, Olga.
Thank you so much. Thank you, Christoph. Thank you, Matt. Thank you, Kelsey. Thank you, Joshua. Thank you, Marco. I hope the connections problems were not too bad. And here we go. I kindly asked my IT team to cut the live stream, that we can maybe continue discussion among the friends without too many witnesses. So, custom live streaming service.